Welcome to another session, Data with Nikk the Greek, and today is the third part of loading big data efficiently. We learned in the past about different file formats, how they're working, how they're performing, and that Parquet and AVRO are more suitable for big data. And today we're gonna learn about a very simple trick how we can improve the loading performance. Also for files like JSON and CSV, which didn't perform very well. And one of the reasons was that the schema has to be interfered in those formats. And what might be the solution? You just define the schema by yourself. So it's really one line of code that matters. And that's where we're gonna have a look a little bit more deeply today. Just as a reminder, if you haven't seen the previous parts of this series, you're gonna find a link here in the screen above in a bit and check it out to just learn the basics, how the different file formats are working. So that means for today, the topics are the following. So we're gonna learn what the schema actually is, how it can speed up your loading time, and then we're also gonna check out some tricks where you can also use it additionally where it can help you. So let's get started. All right, let's jump straight away into VS Code. And as always, we are starting with our data set, which look like that. So we are generating 10 million rows in 8 partitions, and we have 6 columns. So an ID column, which is just going up from 0 to 10 million. We have a date, a timestamp, and then an ID string, which basically just a string out of the ID, which is a big int, and then the first and the last value out of it. So a very simple data set. And the first thing we want to talk about a schema. How you can see the schema of a data frame, you have two options. You just type the name of the SDF and then it gives it to you more like DDL schema like, or you can also get it as a struct type, which Spark usually has a default for the schema definition. And basically the schema consists of three things: the column, as we learned also previously, then the type. So for instance, here we have an ID, then we have a long type, and then we have something here false. So basically it says are null values allowed or not. So in this case, default it says, okay, it's not allowed. And well, if you want to define the schema, I found here a very amazing link where you have also mapping between DDL and the struct type. But basically you have two ways of defining a schema. So the one way is here to say, okay, a DDL schema. So if you want this nullable, you have to just add not null. In this case, I want to allow nullables. And if you want to do the same thing as a struct schema, you have to import, let me show the import shortly, PySpark SQL import types st, and then you can use those type classes which Spark is providing. So in this case, we need a struct type and then define the struct field with the different types in here. I personally, that's my personal opinion, I prefer the DDL schema even for nested ones, because I like to work with strings. I like to put it maybe sometimes to the config, and that's way easier than doing with a struct type. And for bigger data frames, I've also seen that it becomes very, very big and long, and then it just doesn't look very clean anymore. Another way also to, which might be even a benefit, if you define it as DDL schema, you have a very easy option also to generate the struct type schema out of it. And you can see in this case, it generates us exactly the same schema as we have it here. So for instance, ID long time true. All right, now let's get into our experiments. So what we're gonna do today is we're gonna go through our four data sources and check if the schema had some performance improvements. I already have executed everything so that we don't need to wait. So the first thing what we want to do is remind ourselves what the loading time was. So I ran it multiple times before. This time it took a little bit longer. Before it took 11.7 seconds as taken as a reference now. So now what I'm doing is I'm checking which schema has been auto-interfered. So you probably still remember, okay, the date as JSONs cannot save dates and the timestamp have been interfered wrongly as a string. Otherwise, all the values have been interfered correctly. And what I'm gonna do is first is, okay, let's define the schema as it has been auto-interfered and see if we have a performance improvement. And tada, what we saw is the loading time is 7 seconds instead of the 11.7 seconds. So it's roughly 1/3 of performance benefit just by defining the schema. And the reason for it is just to remind ourselves going to the Spark UI. Let's search for the loading part. So here you can see in the Spark UI that we have 2 jobs. So the first job is interfering the schema, which takes 5 seconds. Well, in this scenario now, I hope it doesn't confuse now with the numbers. And the second one takes basically only the loading time. So that means in this, well, you can easily calculate it. We have an improvement of 5 seconds, 1/3. And we only see one job in this case. So now, of course, we have an issue. So that's how the data schema has been auto-interfered, like as we defined it here. But actually, we know that this one is not a string and this one is not a date. So basically, it's not the correct baseline to go for. Normally, what we would have to do is for JSON, we don't have any other chance. We have to cast the data frame. And what I'm gonna do is I'm casting here the date and the timestamp to be a timestamp and a date. And afterwards, I'm also doing just a select statement to order the columns correctly, because you see that in this case it isn't. Last time it ordered me the columns incorrectly for some reason. No, wait, this is where I defined the schema. Here you can see that the columns have been ordered wrongly, so I just added a select statement to also show that the columns are ordered correctly. And we do the same thing by defining the schema in advance. So also with schema definition, we have to define, we have to cast, because those columns cannot be interfered, and then check the performance again. So in this case, we of course are a little bit slower, but still I'm gaining 3.5 seconds just by defining the schema, even if I have a casting or some kind of transformation in this case afterwards. Looking also into the Spark UI, what's happening here. So we have again, even with the casting, the 2 jobs running, and then again we have only 1 job running. And basically you can see the time also here is the same, so only the first job of the 4 seconds is basically disappearing here. So, but now, I mean, for you guess like, okay, this casting, that's like totally annoying. Do I really have to write all those lines to get to my goal? Of course, the trick is no. So basically, what you can partly do for schemas, I'm gonna show in a bit later why partly. So you can just define in your schema also the casting itself. So you can say, okay, the date is a date and timestamp is a timestamp. And it does the whole casting for you. And this is also quite performant. So instead of 14 seconds, you even have a slight improvement, at least in VS Code. Let's check out if this is also the case in the Spark UI. So load JSON with schema. So we have 13 seconds versus the casting of 15 seconds. So even a little bit higher improvement. So, and what we're doing now is, the same thing with CSV. So basically here we are looking again on initial state with the CSV. So we have a loading time of 25.2 seconds, whereby we are only looking now into schema interference. Because the concept even with non-interference is pretty much the same, just that you get a different schema because you're only loading the first line. And if you're doing now the auto schema, we can again see, okay, here the performance is significantly better. And I mean, it makes sense because with CSV, again, you go through all the CSV, but this interference is eventually more unperformant than with the JSON. So we save here more than 50% of the time by taking the schema which is auto interfered by CSV again. So looking into the Spark UI, we're gonna see something similar as we saw before, just with the difference that we have here 3 jobs when we're loading without schema. So this job is loading the first row, then this one is checking the whole data frame, and then this one is basically doing the loading of the data. And here I want also to show something interesting, which I just realized before. Okay. I thought I saw here another task which confused me. Here. So it seems like it's getting the first row of the schema definition already here as an input. So somewhere there's coming like another row of data. I'm not sure where it's coming from exactly, but the only way I can imagine it, it's coming from the previous job. And this previous job is the loading the first row of the schema. So, and with the auto schema, we see again, okay, those 3 jobs are becoming 1. So basically only the third one remains. Okay, the third one takes a little bit longer in this case, but some deviation is sometimes always okay. Then what we're doing again is same logic. We, of course, want our target schema. So here again, we see we do without schema definition. We have 23 seconds, so the casting didn't take too much time. Also with the schema, we don't have a significant longer time with the casting. And afterwards, we define the schema again. And here we have also nearly the same time, like a little bit faster if we define the schema and let the schema do the casting for us. And also looking here into the Spark UI, you see here that we load the schema without manual casting, and then with casting we have here 1 job, and then with the final schema we have also 1 job here. And this pretty much speeds it up. Actually, in the Spark UI with the schema definition, it seems to be even a little bit slower, but it saves you a lot of effort to defining all those lines of code to transform the schema. So now you're asking yourself, all right, we had like from 11.6 compared to 25.2 seconds with the even expected schema, like huge performance. But how about those fancy big data formats like Parquet? Can they become even faster? And actually, you're gonna see actually it can slightly. So here we have a Parquet file for 1 second. And then we have here 0.6 seconds. It depends on the use case. Sometimes it's also a little bit less. Like now in this run, actually this run it became also quite fast again. But depending on the size of the data, it becomes a little bit less. Because what we are basically saving, if you're looking into the Spark UI, so we see here the Parquet file. And remember that the Parquet file, the first part, what we're doing is we're basically loading the schema out of the footer of the Parquet file. And that's why we have here also an additional job. And this job is the one which we are actually saving. So here you can see basically we are saving 10%. So of course, if the file gonna be bigger, of course the loading time gonna be the biggest part. But if you're gonna have a lot of small files, it might be again valuable to define the schema. Exactly. We also did the same thing for AVRO, so I think you can imagine that the code gonna be quite similar. We load the AVRO, and we see it's one job, 3 seconds. We load the AVRO with the schema, and apparently also it got some slight performance improvements here. So load AVRO with schema. So we get here 2 seconds out of it. Let's also have a look into the Spark UI for that. So we can see here 1.6 seconds. So in my experience, actually, it wasn't way faster, but in this case, it became a little bit faster. But usually, AVRO doesn't really have a performance improvement because the schema is directly loaded as it's in the header, not in the footer like with Parquet. Actually, I'm surprised that in this case, we had such a performance improvement because before I couldn't see any of it. So let's maybe run it one more time to see what's happening there live, as it's quite fast. So here now we need 5.5 seconds, and then let's do the same thing. There, it might be that my laptop doesn't want to be that fast today again. So 5 seconds, and with schema we have a slight improvement of 4 seconds. So indeed we have here also some small improvement. Okay, that's actually all about the schema improvements. One thing I would like to talk about before we finish up is some hints about the schema. So we saw that we interfered the schema already in the beginning for JSON and for CSV, so to just do the casting for us. And you might feel, okay, there might be some use of using it. So let's have a look on the Parquet first. So here we're loading the Parquet file and show the schema as we expected it. So now what we can do is, for instance, we see, okay, I don't need all the columns, I just need a few of them. So you can just adjust the schema and it take care of the columns which you actually need. Of course, take care. So it's really important that you define the schema correctly, because this can also go wrong. If you define the schema and want this performance improvement, if you forget or didn't realize that there was a schema change, you might lose data in your ETL pipeline. So there can be also like a small disadvantage. So it's really worth to also check like what's your performance improvement out of it. Usually for CSV JSON, I see the performance improvement very big, as you already saw it. For Parquet, there might be also reasons to not define the schema if it's properly defined in your pipeline and in your file. Then what can also do, there might be reasons where you need it. You can also add a column which doesn't exist in your Parquet table, and then it gonna add a null value. And sometimes you have the case that you know, okay, the schema gonna be changing, and you don't want to help to handle null values, or you have Parquet tables with different schemas to do schema changes, etc. Also for JSONs, it might be interesting because you have the different JSONs, and then some JSONs have like a further nested structure, because some APIs, depending on data availability, might not give you the full JSON schema. And then by defining that for all the JSONs which you're loading, you can basically avoid also this handling of null structures with if else and so on, but just a very simple line. So that's like a good benefit of defining the schema and do this. Also important to see is that for AVRO and for Parquet, we have schema enforcement. So if, for instance, I decide that I want to make out of the big int an int, it basically gonna fail. And the same thing gonna happen also for AVRO. Also, another thing, like we talked about casting the schema in JSON is CSV, and it's partly possible. So for instance, we have here a CSV which we are loading, and we see that we have this format. And now, for instance, we want to say, okay, as we did before, basically. So now out of the ID, make me a big int, and this column should become an integer. This column should become, those columns should become a string. And it's like possible without any issue. So even if you want to, even if it was originally string, I can make it half-half. But we can also do the same thing with JSON, of course. So here we load the JSON with the auto-generated schema without defining the schema, and now just define the schema as we did before in the experiment, and gonna be casted properly. But that's where I wanted to say the but actually. So if you now try to do what we did before by defining the ID string as int, because there's some schema definition in JSON available, you can screw things up. So for JSON, it partly works. So here in this case, instead of making it to an int, it basically adds null values. So that means if you really want to cast this column ID string to an integer, you basically have to do a proper casting, and then you end up with a JSON. And with that, let's come to a short summary. There we go. So we looked today on different formats, and we saw that especially for JSON and for the CSV, the schema really brought a big performance. So if you go with auto schema and define a schema which is auto-generated, we had like 30% of performance improvement. Also, if we compare like a fair comparison of casting it correctly and then do the casting with the schema, also there we had like a 25% of improvement. Also with CSV, we saw that the improvement was even higher. And normally you have the case that you don't know how the schema was originally, you just take the schema out of the CSV. So usually this is gonna be the case you're gonna be looking like, and that's over 50% performance improvement. But also here with a fair comparison, we are pretty much on pretty much exactly on 50%. Then for Parquet, you have a slight improvement. And here we don't have any difference between auto-interfered schema and the actual schema, because the schema is safe in Parquet. And in AVRO, so I experienced in my first experiment no difference. Now in the video we saw that we have some difference, and yeah, but so for AVRO the difference gonna be usually quite low. And with that, to just sum up, schema reduces the loading time, especially for non-schema enforced file formats like CSV, XML, which we haven't considered today, and JSON decreases the loading time significantly. AVRO does not have a big impact, and and the schema can also be used partly for casting, ignoring columns and add null columns, as you saw. And with that, thanks a lot for watching today. I hope you'd enjoyed this deep dive session. And as always, like or comment below, and also subscribe to my channel. You're gonna find below a red button where you can just click on it, and you're gonna be subscribed to stay tuned for the next videos. See you soon.